Okay, second unit is called modeling distributions of data. Like I've said, it's mostly numbers, so it's going to be pretty different from the first unit. The things that we've already done is we've looked at percentiles and estimating percentiles, and we've talked about cumulative relative frequency graphs. And so we're not going to do that again today. And then we're going to start instead with that third one. We're going to look at what's called a z-score, and then we're going to talk about adding, subtracting, multiplying, or dividing by a constant. One thing to remind you of, this is the first page of your notes always. I think this is a great resource for when you are studying for a test. Like, these are all the things that could be on your test, so just make sure you look through that list and you know how to do each of them. And also, I try to put the things that you need to know how to do on the calculator. So there will always be that as well. The other thing to remind you about, the beginning of the packet always has extra multiple choice practice. I find that multiple choice tends to be tougher than free response for students, and so you always have that. Somewhere I put the answers. So in this case, it's the bottom of the third page. The answers are there. If they're not in the packet, then they'll be on Schoology somewhere. This is where the notes start. Like I said, the first page is all about percentiles and cumulative relative frequency plots. I don't want to talk about most of this. There's a few things that I want to write down, though. First thing that I want to write down is that remember that we are at a percentile. We are not in a percentile. So you are not in the 50th percentile. You are at the 50th percentile. And that's because a percentile is a boundary. It's not a region. A percentile is a single value. It is not a region of values. Similar idea to something that was on your test that tripped some of you up. Similar to IQR. IQR is a single number. It is not a range of values. Just like percentiles, single value, not a range of values. Other thing I want to talk about, when we look at a relative frequency graph like this, I could ask you, what part of the graph is the steepest? Or the flattest? And then, of course, what I care about is what does that mean? So I'm going to talk, I'm not going to write this down, but I would suggest you write it down. If we talk about what part of the graph is the steepest, the context is points per game for 486 NBA players in 2016 to 17. Steepest would be like 0 to 5 or 5 to 10. What does that mean about points per game and these players?
Most players would score from that segment.
That's where most of the players are. Most of the players fall between 0 and 5 or 5 and 10 points per game. If we look at 30 to 35 or 25 to 30, that is very flat. What does that mean about points per game in these players?
Not a lot of players are scoring that.
Okay. Very few players fall there. And then you could be asked, like I said, to estimate Q1, Q3, IQR, that kind of thing. Comfortable with those graphs, both making and using them? Okay, let's move on to the next page then. This is the new stuff. Okay, Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? That is, relative to other kids of the same ages. Who is taller? So if we put Macy in a room of 3-year-olds and Brody in a room of 12-year-olds, who is taller compared to their age group? According to the Centers for Disease Control and Prevention, the heights of 3-year-old females have a mean of 94.5 and a standard deviation of 4. The mean height for 12-year-old males is 149 with a standard deviation of 9. Okay, so we don't technically know how to do this yet, but there are some things that we can take a look at. If we take a look at Macy, it's probably a good idea to take her 100 and subtract that average. So we know that she is 5.5 centimeters above the average. Likewise, for Brody, if we take his 158 and subtract the average of 149, we know that he is 9 centimeters above the average. So looking at those two, we might initially say, well, Brody is taller, right? He's 9 centimeters above average. His sister is only 5.5 centimeters above average.
And I believe this sounds like where standard deviation comes in.
Okay. We do need to take into account the typical deviation, the typical amount that these heights deviate. If we take a look at this standard deviation of 9, using Brody, he is 1 standard deviation above the mean. Right, that's just his 9 divided by the typical standard deviation, or the standard deviation. If we take Macy instead, she's 5.5, but the typical, or the standard deviation is 4, so she is more than 1 standard deviation above the mean. So who is taller relative to their age group? Well, it would be Macy, bless you. Because we took a look at how far she was above the average, and then how does that compare to the typical variability? What we just calculated is what is called a z-score. So the way you calculate a z-score is you take an observation, like Macy's 100, you subtract the mean, and you divide by the standard deviation. So if we did it for Brody, we took his 158, we subtracted 149, and we got 9. And then when we compared that to the standard deviation of 9, that told us 1. So what that z-score tells us is the number of standard deviations away from the mean our observation is. Like we saw above, Brody is 1 standard deviation taller than the mean. Macy, we didn't actually calculate hers, but her z-score would be a little bit bigger than 1. Okay, the whole point of a z-score is to get rid of units, to standardize. So z-scores get rid of units. They allow us to compare observations from different distributions. So let's say you scored a 75 on the test, and you want to know how you did compared to your friend in Mr. Plate's class that got a 77. Does that mean necessarily that your friend did better? Well, they got a higher grade, but maybe Mr. Plate grades differently than I do, right? So you really can't compare them like that. So you would calculate a z-score. You would take the mean of the two classes, the standard deviation, and that would tell you comparatively how you did to the people in our class versus your friend in their class. That makes sense? Okay. A few things about this. The sign of the z-score. Positive z-score scores above the mean. Negative z-score is below the mean. So Brody is 158 centimeters. He's taller than the mean. That's why his z-score was positive. If he was shorter than the mean, though, his z-score would be negative. Okay. Questions on z-scores before we actually do it? Okay, so let's take a look at this example. The single-season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961, Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In an absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters, quality of pitchers, hardness of the baseball, dimensions of ballparks, etc. To make a fair comparison, we should see how these performances rate relative to other hitters during the same year. Okay, so if we look, the number of home runs that these players have gotten is going up, of course, because they're breaking records. But what we also need to notice is that the mean or the average number of home runs is also going up. So yeah, while Barry Bonds had the highest number of home runs, the average was the highest that season also. And the standard deviation is going up. So really, is he the best relative to those 4 players or relative to the people that he played with? When it says calculate the standardized score, what it's asking us to do is calculate a z-score for each player. What I want you to do is in your partnership right now, one of you do Babe Ruth and Roger Maris, the other one do Mark McGwire and Barry Bonds. So decide between the 2 of you who's going to do the first 2 players and who's going to do the second 2 players. I would also like you to try this problem here, this 2001 one. So take 5 minutes, do both of these, try the second one at least, and we'll come back together. Here is what I got for the first one, for the 4 z-scores. You guys agree? Okay, and you showed work of some kind. I don't need you to show work for every single player, but just at least once. Okay, what does this tell us in general?
Babe Ruth is still statistically the best.
Okay, Babe Ruth statistically is the best compared to the other players at that time. Second one, asking us to interpret. I would say something like Mark Grace scored 0.48 home runs below the average in 2001. It is very important that you interpret 0.48 as below the average. I don't want you to say negative 0.48 away from the average. That doesn't make sense. 0.48 below the average. So then if we set up using the z-score formula, we get 0.48 is equal to number of home runs, which we want, subtract 21.4 over 13.2. If the average is 21.4 and we have a negative z-score, you should have gotten an answer less than 21.4. If you got something greater, that would tell us that something went wrong. I got about 15 home runs. You guys agree? Okay. We okay on z-scores? Okay. Last thing I want to talk about is computer output real quick. If you were given this output, you could be asked something like, find the z-score for this observation. And so what you would do is you figure out what it is. So it looks like it's 43. And then the output gives you the mean and the standard deviation. So you would then subtract the mean, divide by the standard deviation. We're not going to do that, but I'm showing you, you need to be able to read the computer output. At this point, we know what all of those numbers mean. So you should be able to take all of them out and use them. Sound good? Okay, continuing on to the next page. On this page, we're going to be doing a little bit of an investigation. We are starting with this data set right here, 0, 0, 0, 1, 2, 3. We're going to start by graphing that distribution. So if we make a dot plot, we have 0, 0, 0, 1, 2, 3. We're going to calculate the mean, the median, the standard deviation, and the IQR. Where would I find that information on the calculator? Okay, how would I start? Kanan?
Put in the list and then go to the top with 1 bar stats.
Okay, put all of those values, please, in list 1. And then you will do 1 var stats of list 1. So please do that now. Rosie? Okay. Did you try it now? Okay, so try it, and if you get an error message, show me and I'll. Okay, so hit stat. Enter. So there's your list one.
Okay, which was this? Which was the symbols?
Okay, so mean should be somewhere near the top, and you should see that the mean is 1. The other thing that I want to remind you is there are 2 standard deviations listed. There's S of x, and there's also sigma of x. Sigma of x is population. We do not have the population, so you're never going to use that one. You will always use S of x, which in our case is about 1.26. If you then scroll down, you should see the 5-number summary. So the median is 0.5. IQR is not listed. You should see, though, Q3, and you should see Q1, and if you subtract them, you get 2. We good on that? Okay. Here's what you're going to be doing in a minute. What half of you are going to do is half of you are going to do 2 and 3. What you're going to do is you're going to add 5 to each of those numbers, and then you're going to find the mean, median, standard deviation, IQR. What the other half of you are going to do is you are going to double each value from number 1 and graph the data and find the summary statistics again. What I want, or what I care about, is add 5, calculate the statistics, and then I want to know in general, what does adding a constant do? Does it change the shape? Yes or no, and how? Does it change the center? Yes or no, and how? Does it change the spread? Same thing with doubling. Okay, so what I want, you're going to do this with your partner. Let's start with adding 5. So when I added 5, those are the new dots that I got. Those are the new observations. All these people over here who didn't do the adding 5, write this down. Okay, what is most important is what we get in 3. So I'm going to move us back a little bit. So we went from the blue to the red. We started with the blue was our original, then we added 5 and we got the red. What was the effect to the shape? None. It's the exact same shape. So if you are ever adding or subtracting a constant, the shape will be the same. What about the center? Center being mean and median.
I'll shift it upwards.
Okay, did it shift up by a number that makes sense or just by a random value?
Find it constant.
By 5. Okay, so the center will shift by adding or subtracting that constant. And then we should be able to see the spread doesn't change. All we did was take the data set and move it. We didn't change the variability. So I guess shape, I should say no change. So the hardest one for people to remember is that if you add or subtract a constant, there's no change to the spread. Again, and that should make sense. We're just taking the dot plot and shifting it. That's all we're doing. Questions on that? Okay, so now we have to take a look or think. We went from the blue to this green one. So people on the left side of the room copy down the green. Hopefully you can see over the sunlight. We took that blue, we shifted to the green. And that was when we doubled. We should notice the shape is similar, but not exactly the same. Well, it's the same shape, but it is spread out more. Okay, so this time, if we are multiplying or dividing by a constant, for the shape, again, there's no change. But we should notice the center and spread both change. The center and spread both change. Do they change by a value that we can predict, or is it random?
It multiplies or divides by the constant.
Multiplies or divides by the constant. So they both multiply or divide by the constant. There is one slight thing to take note of. We've only talked about this once, but if we remember, variance is standard deviation squared. Variance is a measure of spread. Because variance is squared, if I were to ask you how would the variance change, it will change by the constant squared. So if we double all of the values, the variance will actually get bigger by 4. If we double all of the values, the variance will actually get bigger by 4. Okay, are we ready to put this into practice? Okay, so let's take a look. In 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. The distribution of distance for one business person was skewed to the right with a mean of 4.8 miles and a standard deviation of 2.3 miles. What are the mean and standard deviation of the cost of the cab rides in dollars? Okay, so the first thing to do is figure out what is the relationship between miles and dollars. Well, the way that we would calculate the cost for any given ride is it's always going to be $2.50, and then it's going to be $2 per mile. I cannot stress enough, you have to write this rule or formula. Don't calculate the mean and standard deviation without having written a relationship. Okay, so then here is the question. If I multiply every number by 2, does that change the mean? If I multiply every observation by 2, will that change the mean? Yeah, that's what we just saw above in blue. So it will change the mean. Will it change the standard deviation? What? Will it change? Yeah. Yeah, just like it did above. When we doubled, that changed the spread. Okay, now we have to think about, if we add 250 to every observation, does that change the mean? Look above. When we added 5 to everything, did it change the mean?
Yes.
Okay, great. So when we add 2, it does change the mean. Or 250 rather. Does it change the spread? No, because all it does is take your dot plot and shift it. Okay, so if we keep those rules in mind then, our new mean is going to be $2 times that 4.8, and then we're going to add the 250. So the mean in dollars is $12.10. Our spread, though, like we said, is only changed by that $2. The 250 shifts the distribution, doesn't change the spread, though. So our standard deviation is going to be $4.60. And all that is the average and the spread in dollars instead of miles. Okay, part B. If he standardized each distance, what would be the shape, mean, and standard deviation? When it says standardize, what you should be thinking in your head is z-score. So if every single distance was changed to a z-score, what would be the mean and standard deviation? Well, and shape. The shape is going to be the same. It's still going to be skewed right. If we standardize, though, There's going to be some observations above the mean, some below the mean. So when we standardize, it will give us a mean of 0 and a standard deviation of 1. So that is important. For z-scores, if you convert the entire distribution to z-scores, you're always going to get a mean of 0 and a standard deviation of 1. Okay, so like I said, I need at most 10 minutes. Sound good? Questions on this before we move to the last topic we need to talk about? Okay, last thing. The distribution of the amount of time it takes Chris to get to work on the bus, including waiting for the bus to arrive, is shown on the dot plot. On about what percent of days does it take between 8 and 11 minutes? Okay, so if we look at this dot plot, 8 is here, 11 is here. Do you think I intend for you to count all of the dots between 8 and 11? Absolutely not. If we look at our distribution, it looks like we can split it into some different sections. Would you agree that they're all about the same in terms of dots? What is the shape of this? What? Thought it? Uniform. This is a uniform shape. Okay, so if we look at all of those rectangles, it looks like there's 1, 2, 3, 4, 5, 6, 7, 8. So it looks like there's about 8 sections. 8 and 11, which is here, takes up 3 of those sections. So we can approximate that about 37.5% of the time, it will take Chris between 8 and 11 minutes. Okay, that above is called a density curve. A density curve traces a dot plot or a histogram. So it's going to be smooth. Why do we do it? Well, it avoids the tedium or the tediousness of estimating or counting the dots. So like we said above, we didn't actually count all of those dots, we just approximated areas. This is really important. The total area under the curve is always 1. 1 as in 100%. We are going to do one last example. This example is a density curve. So you got to imagine as if there were a dot plot there. And you'll notice density is on the y-axis. Density is kind of like relative frequency. You take the first of 2 different train routes that arrive. Each train runs on a precise but 20-minute schedule. So on the x-axis is the amount of time that you wait. So this tells us that you can wait anywhere between 0 and 20 minutes to get a train. So we want to know, what is the probability that you wait less than 5 minutes? Okay, probability you wait less than 5 minutes. What that's looking for is if this is 5, less than 5 minutes is this area. So that's what we're looking for. That area is what we need in part A. Okay, so we need that area. First thing, it's area of, what kind of figure is that? Trapezoid? How do you find the area of a trapezoid? What is it?
1/2 b2 minus b1.
You're very close. 1/2 height. What do I do with the bases? add them. So 1/2 height, base 1 plus base 2. The bases are always what are parallel. So in this case, this is one base, this is the other base. So we are going to have 1/2, our height is 5. And then we don't actually know either of the bases. We're going to have to find those. Okay, well, we wrote above, if we remember, the total area is 1. So the area of that entire triangle needs to be 1. So area of a triangle is 1/2. The base is 20. The height we don't know. So I can use that fact to figure out that the height of the triangle is 0.1. Okay, so if that height is 0.1 then, this height at 10 will be 0.05. So then this height will be 0.075. Okay, so now plugging in, one of the bases is 0.1, the other one is 0.075. So this probability then is 0.4375. So about 43% of the time, you would wait between less than 5 minutes. Is that okay? Okay, lovely. Next, between 5 and 15. So our 5 is here, 15 is here. This is the area that we're looking for. Again, it is a trapezoid. So we have 1/2. This time the height is 10. So remember, it's the distance between the bases. The one base is 0.075. The other one we need to find. If I have this base of 0.05, if this is a height of 0, this one is 0.025. And this, how nice, ends up being 0.5. So half the time, we would wait between 5 and 15 minutes. You should do a mental check. If the entire figure is 100%, does it look like the blue part is about 50%? Yeah. If we got something like 10%, that would tell us we were wrong. We are not going to do part C. We're just going to stop there. Okay. Questions for me?